Welcome to ACI, the Network Made Simple learning series. In this video, we will cover Module 5, Extending the Fabric, Chapter 1, ACI Anywhere Overview. One of the main goals of IT is to connect users and devices to applications anywhere they may be, and the network plays a fundamental role to connect the digital business, since it touches everything, whether that means a single campus or multiple data centers, one or many clouds, and multiple form factors such as physical, virtual, and container-based platforms integrating Layer 4, Layer 7 services. With no exception, all of them need to have the network provisioned, managed, and secured somehow. And under this hyper-diverse and hyper-distributed landscape, we often deal with inconsistency, slow provisioning times, and endless troubleshooting windows for connectivity services due to separate people managing the network through different tools and technology types. With ACI Anywhere, you can run ACI in one or more pods, edge or remote locations, and clouds, even with no Cisco hardware, providing a consistent and automated network operations model. However, there may be other types of networks in your data center and cloud environments, such as NXOS-based ones, SAN, and many others, which may not only need consistent management as well, but also automated interconnect capabilities across sites and smart analytics and correlation to prevent potential network outages. This is why Cisco released the Nexus dashboard, which is a connectivity platform that consolidates multiple services for your networking environments, such as automated interconnect between clouds and sites, smart visibility and correlation, amongst many others. With this being said, when you integrate your ACI sites into the Nexus dashboard, you can get automation for multiple sites and clouds, a consolidated operational model for all of them, and predictive analytics that can help you minimize risk. Let's now take a look at how ACI Anywhere and the Nexus dashboard can work together to accomplish this. If you remember, a single ACI site is represented by an APIC or APIC cluster, which can live either on-prem or in the cloud. However, if you have multiple ACI sites running in different data centers or clouds, you may potentially end up managing different APICs in different parts of the world, along with their data center and cloud interconnect configurations. That's where the Nexus dashboard and its orchestrator service comes in, which can centralize the management of multiple ACI sites, as well as NXOS-based ones as we covered before, automating inter-cloud and inter-site connectivity and following a configure once, deploy anywhere model. In this module, we will only focus on ACI fabrics, both on-prem and cloud-based, and show you how Nexus Dashboard Orchestrator can enable multi-site ACI topologies in a few minutes. Let's start our ACI Anywhere journey with the SingleSite fabric extension options. Throughout this learning series, we have mostly focused on a single-site, single-pod configuration when talking about on-prem installations. However, through the same APIC or APIC cluster, we could extend the centralized management and automate VXlan connectivity to other data centers and rooms, branches, and even environments with no Nexus 9000 switches by using features like MultiPod, Remote Leaf, and Virtual ACI or VPod respectively. All these models can help you extending the network consistently across locations and providing an easy way to implement use cases such as active-active data centers, DRPs, seamless VM mobility across L3 networks, co-location environments, and data center migration amongst others. For any of these single-site fabric extension models, we need to consider that an extra 50-byte MTU will be required in your transit network based on your endpoint payload in order to avoid fragmentation. This is because payload packets will have a VXlan header added as they enter their ACI pod or remote location. In addition to this, we will need to configure DHCP relay on the far end router receiving the remote connection so that APIC can automatically assign an IP address from the TEP pool of those remote devices as we will learn today. Let's now start taking a deeper look into MultiPod. MultiPod is useful when we have different rooms separated by an L3 domain or different locations close to each other. If you are familiar with cloud terminology, think of each pod as an availability zone. In this example, our data centers are located in New York and Boston. Through ACI and MultiPod, the same APIC cluster can manage both locations and automate VXlan between them. If we only have two locations, like what is shown in this case, and have no plans to add further sites, we could simply cable our spines back to back, and ACI would automate an OSPF underlay and a VXlan overlay between them, without the need to worry about MTU or DHCP relay configurations on intermediate external devices. This is commonly used in scenarios where you may need high bandwidth connections, such as 100 gig or 400 gig for example, between isolated rooms, or where you already have a dark fiber, optic transport, or NCS installations between locations. It is important to mention that back-to-back multi-pod topologies requires ACI versions 5.2.2 or later. If you want to scale beyond 2 pods and up to 12 pods, the traditional multi-pod topology can be leveraged. The main difference when comparing to the previous scenario is that an inter-pod network, or IPN, is required. The IPN is a routed network which needs to have a maximum of 50 milliseconds in round-trip time and multicast support for broadcast on non-unicast and multicast traffic. The spines on each pod will physically connect to the IPN first hop device, which can be any device as long as it can run OSPF and receive tag traffic on VLAN 4, which is usually done through a sub-interface. This is because ACI will automate the OSPF underlay configuration on the spine side on each pod, and the corresponding IPN first hop devices are expected to match such configuration settings. Keep in mind that the IPN nodes are not managed nor automated by ACI. Therefore, you will need to manually configure OSPF with VLAN 4 in those first hop devices. In addition, please remember to make the corresponding MTU adjustments throughout the IPN and set DHCP relay on the far end router as mentioned before. As a result, we will get a single APIC cluster managing multiple pods centrally, each with their automatically discovered spine and leaf nodes, effectively expanding the network to multiple locations while keeping operations consolidated. We will cover the configuration details of multipod in Chapter 2 of this module, so please stay tuned. Let's now move on to talk about our second option for single fabric extension, remote leaf. With remote leaf, we can interconnect up to 64 locations with 2 leaf nodes each, automating VXLAN across all of them. This is useful when you have a smaller site, such a co-location environment, branch, or brownfield, and you don't want to invest in a fully blown ACI fabric with APICs, spine, and leaf nodes. Remote leaf nodes are assigned to a pod, so that they can leverage spine functions whenever they need it. You can have both multipod and remote leaf working together in a single ACI site. Just as with multipod, you need an IPN with a few requisites. First, we need a maximum of 300 milliseconds in round-trip time and a minimum of 100 megabits in bandwidth, and just like multipod, we will connect our remote leaf nodes on the far end to the local router or first hop IPN device, which should support OSPF and the DHCP relay as well. In this case, multicast is not needed for BOM traffic, since head-end replication is used instead. As a result, we get a single APIC cluster managing multiple remote sites or branch offices centrally, with automated discovery and network extension. We will cover the configuration details of remote leaf in Chapter 3 of this module, so make sure you stick around. Finally, let's now briefly cover our third option for single fabric extension, virtual ACI or vPod. With vPod, you just run a virtual spine and virtual leaf in the remote location, running vSphere as a hypervisor and leveraging AVE as the data plane on each host. This way, for environments where no Nexus 9000 hardware is available, you can still automate VXLAN connectivity while keeping the same centralized management model. Just like with the previous 2 scenarios, virtual ACI or vPod requires an IPN with less than 150 milliseconds in round-trip time, and you will have your virtual spines connecting to the first hop ISN device through OSPF as well. It is important to mention that when using vPod, the vSpine and vLeaf are not in the data plane. However, they are leveraged for control plane purposes, COOP, and other ACI functionalities. Virtual ACI or vPod is commonly implemented for policy extension to co-location environments and brownfields, as well as for migration purposes, and it requires a specific license for the virtual spine and leaf cluster, as well as for each AVE host. As a result, we maintain our single APIC cluster managing virtual ACI pods as shown in this topology. As of the recording of this video, you can scale up to 6 vPods. Just as on-prem, and as covered before, we may also have cloud ACI deployments, where an APIC represents one or multiple cloud regions per cloud provider, automating connectivity between VPCs and VNets for IaaS, PaaS, SaaS, and third-party services in the cloud. With this being said, a single cloud APIC and all its regions can be considered similar to a multi-pod deployment in the cloud, since it is automating inter-region connectivity within the same cloud provider. After an overview of ACI's SingleSite fabric extension options, please join me in part 2 of this chapter, where we will go over some multi-site ACI concepts and topologies leveraging Nexus Dashboard Orchestrator.